We're going to construct a peak model for a given sample, and we're going to do this using two spectra that have been measured at different angles, where the sample has been tilted so that the surface sensitivity of XPS is exploited to change the apparent relationship between peaks. The first thing I'm going to do is calibrate the energy scale with respect to one another. The absolute energy scale is not going to be calibrated. It's just a question of using the calibration option and aligning, making sure that these peaks here, which should be from a ruthenium 5/2 peak, align in position. And although they're very close, I think I will just do a very fine adjustment using an option on the calibration property page, where if I hold the control key down, I can slide an image of one spectrum relative to the other. So what I would like to do is just make a fine adjustment and say apply. So now I have my data aligned, and the idea of aligning the data is so that the calculator property page can be used to create a sequence of different spectra. The different spectra are used to understand the relationship of these peaks and how they change as the proportion from one spectrum to the other occurs. So this one is just over halfway through the sequence, and you can see that as I step up and down that I've now got something which looks like a doublet that comes from the ruthenium 3D. So let's just save that one. So I've now found another position in this list of different spectra where the shape is very characteristic of the carbon only, and I've removed from the data any sign of a peak that would be corresponding to ruthenium 3D 5/2. So this is expected to be representative of C1s peaks only. So I'll copy that one. So now I've got two spectra, and the idea is that these two spectra, now calculated from the original two spectra, can be used to better understand the peak model. These two spectra that have just been calculated can be used to reproduce the original spectra, the original spectra of the first and the last in this list. So having overlaid these in the active tile and selected the two that we want to target, generate spectra, and if I overlay these 4 VAMOS blocks as created, these are the original one, the reproduced spectrum, which is the sum in a least square sense of these two components, and you can see here that they reproduce exactly, and that's as you would expect. And similarly the second one has done the same. So there are actually 4 spectra there, and the reproduction is the red one, and it is an exact reproduction of the original data by summing these two components. So if we can create a peak model for these two components, we know that the peak model will then apply to the original spectrum. So what we'll do is create a peak model. First of all, we'll do the carbon 1s, and if I enter some peaks here, just give them a sensible starting point, say fit, we've now got a peak model that is based on 3 components, and they are all going to be carbon 1s components. Now in this case we've got, again we'll put a background on, and we've got multiple peaks here. However, these are doublet peaks, so that makes life a little bit easier in the sense that we know this is a ruthenium 3D, and I'll copy that and paste. And then I will create another one, because this is a carbon 1s, I believe. And then we still have signal that doesn't belong to either of these, as it would seem. So let's see what this looks like if we start to introduce a constraint, and the constraint I'm going to enter is a relationship between the doublet pair, the 5 halves and the 3 halves of the ruthenium 3D, and you can see that there is an excess signal even here. So what I'll do is I'll copy these ruthenium peaks and I'll paste them, and then what I'll do is I'll move, and I've still got the relationship between the ruthenium, so I'm assuming that these are related to ruthenium, and when I say fit I then get a peak model. And let's see now, let's just adjust this a little bit more. And say fit again. And now I've got a peak model where I think this is a carbon 1s. And I think it's a carbon 1s because when I overlay these two, that I've got a common peak here. That this peak from the C1s envelope appears to be about the same position as this one, so I'm going to now construct a peak model for the original data, and it's going to be based on what I've just seen from those components. And so what I'm going to do is I will take the carbon 1s, copy all, and I will paste, and then I will take the ruthenium peaks and I'll say copy all, and I will say paste, and so I've got a peak model which has doubled up on this carbon 1s, so I'm going to delete that one, and on the basis that I fitted those component peaks, I'm going to lock all of these together in terms of position, and we'll say fit. And now I have a peak model that fits the data, and I've constructed this based on dividing the data into two components that are representative of different and more simplified envelopes that have been derived from the original data. I suppose the last thing I ought to do is then take that model and propagate it. I won't fit it straight away. I'll propagate and I'll copy all and say paste replace, and then say fit. And again I've got a peak model that works for both the original data at the different angles.